So I'll be touching brief on the classical ML and show you intuition about how deep learning works, and also talk on the intuition of the reinforcement learning. So as you all know about supervised machine learning, the classical ML algorithms like linear regression, where it's like a linear plane is being created if it is a multivariate thing. If it is SVM, then a non-linear plane is being created to separate the things for classification or make a complex function to predict a value. Or if things are more complex and data is highly unstructured kind of stuff. We also have decision trees, and there are some limitations of decision trees. So then we use random forest to average out the voting of decision trees, and then we have boosted forest to take care and have higher weightage for the unclassified things. So that's what supervised learning is, and that important thing about supervised learning is that we need tag data. We need the mapping from X to Y, that okay, if this is a picture of a dog, then a picture should be equal to the dog. That's the X to Y mapping. So that's what we require for supervised learning. And those algorithms I mentioned are on the classical side. On the unsupervised side, what we are primarily trying to do is like remove the noise out of the information that we have. Like there are so many features, like sometimes we are working with a large data set, we have hundreds of features, and a lot of things will be either highly correlated or will be adding noise to the thing. So then what we do is like we represent the whole data into n dimensions, and then try to remove the features directly or indirectly, or rotate or turn the space of the dimension in such a way that we are able to represent the whole thing in a much compressed way, and it also makes sense. So we use algorithms like PCA, ICA, we have K-means algorithm. Then we also have TSNE for visualization. So those kind of algorithms are done to represent the same thing in either 2D or less dimensions than there were earlier. Now comes the other part, the deep learning. So what's the necessity of deep learning is a question in itself. Like, what is the limitation of those other algorithms that we're talking about? So in a generalized way, what are we exactly trying to do? The mapping from X to Y. So in between there is a function which maps the X to Y, and every algorithm has certain limitations when it comes to the data. So now, how does deep learning change the whole game in itself? In this generalized architecture, you must be knowing that there will be an input layer where we give the data that we have. So sometimes it's just a 2D array where every row represents a set of data, and either it's an image, so it can be 2D or 3D depending on color or just grayscale image. Sometimes it's audio also. So all that is given as in the input, and in the hidden side, we can play with as many layers as we want. And so every layer that we add is adding a non-linear function to the whole thing. So the more deeper the neural network, the more complex and non-linear functions are we creating. And we have this flexibility with this. We don't have that with other algorithms in the way that we have with this one. So deeper is equal to more non-linear, and having more neurons on one layer means we can again have mapping to more complex functions. And then on the output, we have the Y variable. So now what is exactly this one neuron is representing? One neuron is representing non-linear function, and it can be anything, and there are a lot of functions. This is the sigmoid function that we have, and its responsibility is to take input and give the output, which is ranging from 0 to 1. And we take this output from a lot of neurons and give different weights according to how one neuron is talking about a particular information. And we use the backprop algorithm to optimize these weights. And we finally find out like which neuron is actually talking more sense, and which neuron is not able to give any information. So these weights change, and we are able to create that complex function that we are talking about to map the Y to X. So these weights are like voting mechanism for the whole thing. So there is this thing called universal approximation theorem, and there's this nice article on this, which I would like to just skim through. It's not loading the images. Okay, okay. So suppose there is this curve, which is, this looks like a random curve to me, which is mapping this x to the y. So when we have this very simple neural network with just one hidden layer, input and output, this function that is finally created is f of x for the given f of x for, I mean, that is allowing us to output the y. If we have multiple functions, then multiple outputs, then these functions are going to be different functions of this x1, x2, x3. So now the sigmoid that we're talking about, that is actually a nonlinear function, and it sometimes it will feel intuitively that how can we use this weird curve to just represent every other curve in the world. But it so happens that when we tweak the values of this bias and weights in such a way, it suddenly is able to approximate different kind of functions. So over here, it is approximating a step function. And this is just like one layer with two neurons. And as we go on increasing the layers and neurons, it can create complex functions as required according to the weights, and weights will be optimized according to the output. So if the output is a step function, then the weights will be created accordingly. So if we see different weights, different outputs, the more complex the output, the whole curve, the more neurons are we requiring to create that thing. So I hope you are able to grasp the intuition that I'm trying to explain to you, that the more complex the curve, the more neurons it is required to represent the whole function. And in the 3D, it looks like this, although it is explaining the same thing. Let's go now, let's try to visualize in real time what exactly I was saying. So now the whole thing is about mapping non-linear functions. क्योंकि linear चाहिए तो linear regression है, but non-linear में we have some issues. So there is this XOR function, very famous non-linear function, that 0 0 it gives 0 output, 0 1 1 1 0 up to here it makes sense. Okay, बढ़ेगा तो बढ़ेगा, but over here when both are 1 it gives 0. So now this is not easy. This cannot be represented by linear regression, just not possible. So for this, there is this sample neural network with just two neurons in the hidden side, two inputs as required and one output. So when we start to train this, if you see initially just with this random initialization, it is not actually giving us the output that we are expecting. Oh, required is 0, it's 0.6, all are like around 0.6. So as we start to train this, and these weights will start to change according to these iterations, these values will converge to what we are looking for, and that's how the whole cost optimization is happening. And it can be stochastic gradient descent or atom or nested row, anything can be there. And over here the parameters are like this, sigmoid functions are being used. And then within like 30,000, it almost converges to what we want. Now let's go over here, and I can actually add more data points over here and see how it is making sense. Okay, let's stop this. So now 1 1 over here, and reds are over here, and it has created successfully a boundary to do the classification or give the output. Now if I add more green over here, let's keep this running. Is it running? Okay. So if I add green over here, it's not going to change anything because the boundary is correct. But if I add it over here, it suddenly changes the whole decision boundary, and now it is able to create new weights and biases to map the same thing. Okay, but now, okay, I had a lot of green over here, and if I want to add a red over here, what exactly will happen? So if I add a red, it is in a dilemma, like how can I represent this red? Like how can I create a boundary to just say that, okay, this red is a red, but it is not able to do it. Uh, and okay, let's put some red, more red, and see how it behaves. So now the whole thing is shifting towards where more red are there. Okay, now it is able to take those red also into the red boundary as well. Now, what can happen if I add more neurons? Let's just try it out and see. So in the hidden, there are two. I add more neurons. I guess I added 6 neurons. I lost the. This whole thing is refreshed. I will just refresh this thing. I'll add more green. So I'm trying to put a red between the green and see how it behaves and can it map it or not. And I'll increase the neurons on the hidden side and see if that makes a difference. So currently I'm having 2 neurons and I'm going to increase the neurons over here. So now if you see, it is, if these decision boundaries are not generalized, this is almost overfitting because it is creating a very specific boundary for only those red points, and this is how we define overfitting. Just remembering the data, there is no generalization over it. Itna remember kar liya, itna kar liya, itna kar liya, and this is not how it actually should be. This whole thing should be red or something should be there. uh, there should be some wrong classification as well, and it is actually remembering everything because we have that many weights to uh, make those complex boundaries that we require. Let's stop this. So that's the thing I just wanted to convey about the decision boundaries and nonlinear functions of the neural network. And again, the same thing how supervised thing works in deep learning. You give an image and it gives an output, and then if you see, we are just creating features out of features. Their input has, like, let's say 100 variables as input, and then we have lesser and lesser features, like, as we have must have read some articles by Kola or Karpathy, that initially it tries to extract the edges and it creates, in the next layer it creates shapes, and then it understands the whole image. So every layer is actually extracting only a certain features out of it, and then use those features in the next layer to create more complex functions out. In the unsupervised side, we have this thing called autoencoder, where we take the input and then give it to the output as well, and then we are just creating a neural network which actually represents the input itself. Now, what's the usefulness of such a thing? Why would we do that? That's not even a business problem in itself. Uh, so by doing this, as I said, that in neural network, we just go on reducing the variables and try to represent the same input in lesser features. So over here, if you see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, let's say, features to represent the input. It's a 2D, but just let's say imagine it's 1D. So 9, then the same thing is represented, not exactly, but it's an approximation, represented by 6 variables, let's say. Then it's the same thing is represented by 5, and over here it's represented by 4. Now the whole information, the image is compressed. It's like, see, it's like image was so big, and then we have suddenly created a very small image out of it, size wise, and then from the same we are creating the image again, which is of the original size. So does that mean that this information that we have is enough to represent the information that was over here? So now the usefulness of this is a bit on the software engineering side, that if you have to, let's say, create recommendation algorithms which work on the similarity on the scale of Amazon or Google, creating search engines and whatnot, then having a compression of data from this to this makes a huge cost saving on the business side. So for certain applications, and now that's like the paisa bachane wali cheez, but there are also other things that we can do with that. So for a lot of other applications, we are actually interested in the compressed information. So that's the whole thing about unsupervised learning. Now comes the reinforcement learning. How is it different from supervised and unsupervised? What makes it so different? So in the supervised, we are very clear, we need the tag data. Otherwise, we cannot do anything. On the unsupervised side, we are interested in representing the whole information in a compressed way. Now on the reinforcement learning, the thing is that we want to do something like supervised, but we don't have the tag data. So then we have this whole mechanism that simulates that kind of system, which is like a supervised thing. It's like a teacher and a student kind of stuff, where a student tries to learn something and then give an exam, but in the exam it does not perform well. So teacher gives a feedback kind of thing that, okay, you need to improve on this, you are going in the right direction, you are going in the wrong direction. And then according to that feedback, the student works again and tries to perform better. So let's take this scenario. It's a very classical scenario that is given in a lot of books, that there are this bunch of ladies who are interested in playing uh, the slot machine in a casino. Now, this is the whole thing how the reinforcement learning works. There is an agent. The agent acts on the environment, and this creates a reward, and the state is changed from ST to ST plus 1. So what is the agent over here? Let's say the lady in the blue dress is the agent, the person who is going to perform an action. What is the environment over here? Environment is the whole casino with having, let's say, 10 slot machines. So now the lady is interested only playing with the slot machines, not anything else. So we have defined our environment. And in the environment also, what she can see, what is observable environment is that she can only look at the pattern that is coming on the slot machine, and only she can, on the action wise, she can only pull the lever. She cannot do much. What's the implication of this? If this is called a partially observable uh, environment, and if I had the environment where I have the complete information, as in I know what is the internal mechanism of the slot machine, what are the exact positions of the gear, if I pull the lever in this way, in this machine, what is going to be the motion of the gears and how it will be, whether it will give me an output or not. If I have the complete information, then I know which slot machine to pull. I just need to calculate the whole thing. But we don't have that. So it's a partially observable universe. On the analogy side, it's like finance, stock market. What is visible to me is just the prices on the stock market. I can see the balance sheet, the profit and loss statement, and news articles. That's the environment that is visible to me. I don't know what is it going in the head of the CEO of the company. I don't have any other internal information which can help me to predict this better. If I knew those things, like what are the next step of the CEO, are they doing any scam or not? If I have that kind of information, I can take steps in a better way. But so my information is limited, and I have to work with this limited information to predict the required thing. So over here, she has just the machine in front of her, the patterns, and she is pulling the lever. Now the question arises in any person's mind, like which slot machine might turn out to be more lucky for me. So we have to go with the random selection, right? Otherwise, unless we have some information that this machine is giving us more rewards than other machines. But let's say we don't have any historical information of any person pulling the lever, and she is the one going to play it first, and she is the only one person who is going to play. So she is the agent. She is going to take the action on the environment, and the environment was in a state ST, and after the action is performed, the pulling the lever, Then the environment is in a state as t+1, and the reward that is generated, like if she wins it, she gets a reward. If she doesn't win it, she has to put some machine to play the thing. So that is a negative kind of reward. So she gets a reward, and that goes into the mind of the agent. So let's say she plays a machine a lot of times, does not get a reward. She understands this machine might not do something for me. So then she shifts to the other thing. So this is like a very common sense kind of thing, but how to put it in a mathematical way, like how to go about exploring the machines in a way that optimizes my rewards. So let's assume that we are going to pull lever k times on every machine, and so the average reward will be going to be summation of these rewards divided by k times. And there comes the concept of exploration versus exploitation. Exploration means that I want to try out different slot machines frequently, so I'm exploring. But exploitation means I'm going to take greedy action, like if I just played on a machine which gives me small rewards, but it gives me rewards, and there is another machine which might give me once in a blue moon kind of reward, but I don't know if it is going to happen with me or not. So I just go and take the greedy action. Greedy action is the taking the action which gives me the highest reward. So we are in a dilemma of this kind, right? We want to go and explore new food in different restaurants. Um, so either we should go to the place that I already know it and serves good food at a good price, or should I go around trying out other 5 restaurants? And I know for sure some way, in my past historical way, that at least 4 out of these 5 is going to be disappointment. So that's what the exploration versus exploitation is. So as we change the value of exploration, so exploration is defined by epsilon over here. Epsilon equal to 0, as in I just take action on one slot machine. I try out different slot machines equally, and then whenever I encounter a machine which gives me reward, I just uh, go on using that machine only. I stop exploring. If I put an exploration of let's say 0.01, it converts into like out of 100 actions, at least once I will try the new thing and see how it behaves, irrespective of how high rewards I'm getting. If I increase the exploration to 0.1, it means I'm going to try 10 out of 100 times. So I'm going to try more things. And so from the chart, based on the problem they defined, it turned out that if you are stuck with the worst or not if you are stuck with the suboptimal return, your chart will be constant and it will be this one. If you have exploration, you will find out new slot machines that will give you more reward. And there exists an optimal epsilon. Of course, if epsilon is very high, you might have discovered the optimal, the best slot machine, and still you'll be exploring and you'll be losing out money. So there will be an optimal value of exploration as well. So 0.1, it so happens in this case, we are not trying to prove that more exploration is better, because then we become, so in our way, in human way, we become the jack of all. We have to develop an expertise into something, so we cannot explore too much as well. So 0.1 happens to be the best in this case, but don't take it that way. Yeah.
Yeah. So when you say when the epsilon is 0.01, it will take 1 random action out of 100, right? Now, when you say 1 out of 100, it means those actions are within one episode, or irrespective of where the episode is ending, one
Right.
in every 10 action will be random. 1 in every 100 action will be random. How is it?
Right. So in this case, in the slot machine case, the episode ends as soon as the action is taken, right? It's just one slot machine pulling, that's the episode in itself.
Yeah.
So in a game like Mario, if you are trying to do it, I think we can try exploring things, and there will be different kind of things to explore, right? As the game is moving from one.
And what about the market point of view?
From the finance point of view,
yes.
exploration, that's an interesting question. let's take it at the end. I think I'll have to think. That's a tough question. So again, on the definition side, episodic task is something like that ends on a after a particular thing. So Mario, we know that there is this stage, and there'll be a lot of stages also. But at the end, it ends. There is nothing like it just continues forever. While a game like PUBG might not end, it just keeps on continuing. I hope my concepts on the PUBG is correct. I've not played it, heard it a lot nowadays. So in that case, we are if we just keep on adding the reward in the infinite case, any action will give us an infinite reward. So we need to penalize it and constrain it in a way. This is geometric progression, which we have read in like 11th standard. So we penalize the future rewards more heavily based on this lambda value. So smaller the lambda, it means if it is just, let's say 0.1, then we are heavily penalizing it. Every reward that we get in the next action is just 1/10 the value that we get in this action. So the more interested we are in the current reward, the nearby reward, the higher the value of lambda. So that is also a parameter to be optimized. There is nothing like perfect value for that. And in this kind, we just sum the whole reward till the end of the stage, let's say. Another thing, there is this beautiful thing called Markov property, where the definition is like state action. Okay. The future state that we are going to get is just a function of the current thing. So it's like I can just look at a person and I can see what is his current state. He has done an MBA in something and something, let's say marketing. And I can be very sure that he is going to pursue a career in MBA marketing and marketing only. He's not going to do some architecture kind of stuff the next day. So I don't need his history also, like kya pada usne, engineering kiya tha, arts kiya tha, I'm not interested. It's an assumption, of course. History plays a role, and in finance also it plays a role. But it's an assumption which makes our whole calculation easy. Although there are some research paper I read, and in that history is also considered. So this is a definition, but it's not necessary to use it also. So when I was saying about the current state and the future state and the action and things like that. So there is this classical example called robot MDP. MDP is Markov decision process, and so in this, the problem statement is like a robot is in a room. Do I have time? Okay. So a robot is in a room, and the job of the robot is to collect the cans that are present in the empty cans that are present in the room. So a lot of people are drinking Coke and they're leaving the can, and the robot's job is to collect the cans. Now there are two approaches to this. Either the robot can just sit at one place and let people drop the can into the collection bin, let's say, of the robot, or it can actually move and lose some battery but collect more cans. So so suppose it's in a high battery state. So they have defined a high battery state and low battery state. In the high battery state, it can either search, go around and lose battery and search, or it can wait and collect it. In the low battery state, it can either search or wait or recharge. It has to recharge because now it's in the low battery state, it can stop anytime, and we want to maximize the reward, so there should be recharge also. It should not stop. So so I'm just trying to explain you the definitions of this thing and how they work. So it's in a high state, it can search, and then the new battery state can be high. If it's in the high battery state, it can search and go into the low battery state. And it's in the high, it can wait and still be in the high because there is no loss of battery. It's in the high, it can wait and also go into the low battery state. But that's the probability of that is 0. Okay, that cannot happen. It's doing nothing, so probability is 0. Right. and the rewards associated with that. So everything has different probabilities based on the historical data. Alpha, if one is alpha, then other has to be 1 minus alpha. One is beta, then other is 1 minus beta. And the rewards associated are different. Like if it is searching, then it might find more cans, so the reward is different. It will be more than the reward of waiting. So this is how the whole definition works. It's in state. Something is state as action is taken as dash, and the probability of being in S dash, the new state, given the state and the action is defined is this way, and the rewards are also defined in a similar way. So then this is called a transition graph, and it's just a visual representation of the same thing. Now, I want to optimize this reinforcement learning problem in such a way that I end up with the highest reward. So there is this thing called value function, and there is this another called policy. So value function is equal to summation of current plus all the future rewards that can happen starting from the current state, and they are also discounted by this gamma. So it's like if I'm going to take BTech as an education, um, so reward of doing BTech, and let's say it's like average CTC of doing BTech. Then after that, I can do MTech. There are a lot of ways. It's like a decision tree in itself. I can do MTech. I can do MS from outside. I can do MBA. I can just do a job, and then there's like one step, and then another step can be something else. I can do PhD. I can, if I was doing job, I can do MBA. If I was doing MBA, I can do job. So I was in state BTech, and I'm trying to sum up the rewards that I can get from BTech to the future states I can be. So that is like reward of being in BTech, the uh, value of BTech, let's say. So now the competitors of BTech can be other degrees that are on the bachelor's level. And this policy function is like a mapping that if I'm in BTech, what is the best degree that I should be, not degree, but is the best action path I should take as a next career step to get the maximum reward. So that's why like lot of people have found out that MBA seems like a good step by just observing other people. It happens intuitively, but like on the mathematical level, if you want to represent it, it's something like this. And also, gamma is a very philosophical thing to me. Like it doesn't make sense. We never plan for like what will be my salary when I be 50 years of age. We always plan it for like next 2-3 years or 5 years. So the importance of nearby uh, state is more important to me than the future state. So that's the whole value function and pi function. So we do the value function over different states, and once we find out different rewards for different states, then we just need to like do a max of the next reward state, then max of the next reward state kind of stuff, and then we find out the mapping for the action for a given state. So that is called a state action pair. It's like a 2D, it can be 3D also, I guess, but it's like a 2D kind of array where let's say one is state and one is action. And so if you are in a given state, you just need to uh, do a max on the row and take the action that gives us the maximum reward.
So, in this example, we did, for example, the two tables that is completed. Can we start with, say, I'm adopting a random policy and start with state.
Right.
So, how will the BTech example works here?
It's an analogy, but yeah, in the actual queue algorithm, it starts randomly. So okay, I think there is a mismatch of that. Yeah, agree. But I hope it also makes sense on some level, right? If you take the different states that are happening next by next, and if you're trying to find out the value of the BTech, that's how we'll do it, right? Okay, yeah, we can discuss more on that. Yeah, there are always this certain considerations where we have a mismatch. So we are in this room. I'm not going to talk more on how exactly it will be done, but we are in this room and we are starting at this 2, and then our aim is to just exit out of the room. So I can exit from here or here, and the whole thing is defined in this way that these are the rooms, and I can move from one room to another. And if I'm exiting, I'm getting 100 reward, and if I'm just moving from one room to another, which is not an exit room, I get 0. So we defined an initial state where the state is like any room that we have, and the action of going to another room. So -1 means that we cannot go into that room. If I'm 0, I cannot go into 0, and there is no connection between, let's say, 0 and 1. 0 is here and 1 is here, so that's -1. The -1 is like not possible, uh, and 0 is I can go, but that's not the exit point. So, and if I'm in 1 or 4, I can go to 5, and that will give me 100 reward. So we initialize this whole thing, and this is like this. So rewards are already given, and we can run a deep queue algorithm on this, and this is called a Bellman equation. And on the generalized level, it's like, what is the reward of the action that I will be taking from this state, and what is the discounted reward of all the future actions. So that's the future reward plus the reward that I'm going to get. So when you run this queue algorithm on this, uh, ultimately you will come up with a queue table like this, and this all represent the value that you're going to get from transitioning from one state to the next room that you can go. So of course, then you have to just do a max function over the row and take the next room that is going to give you the max value. So if you are in room 3, you see that there is 80, 51, 80. You can go into this and this also. So if you are in 3, 1, you can go from 3 to 1 and 3 to 4, and both are going to give you take you to the 5 in the same number of steps. So both are also having the same value of 80. And if you are going from 3 to 2, you are going backwards, so that value is less. So this is a policy for the action that you have to take. Now, that's the whole thing about reinforcement learning and what are the different applications for this. So in finance, there are some research papers on making indexes out of it. So currently there are different ways of making indexes to find out the weights of the holdings of the stocks in a portfolio. But apparently it can be also done by reinforcement learning, where you're not using some gradient descent kind of optimizer, but you are allowing reinforcement learning to figure out that what kind of weight should be there to maximize the future rewards.
So in finance, why do we not use it for predicting?
That's very tough question, because deep learning requires a lot of data to train, and there are a lot of things to train. And what is happening with finance is that they want explainability.
Yeah.
In deep learning, it gets very difficult to explain the whole thing. So we have models in our company which we can train with deep learning. The data is sufficient, but we still go with non-deep learning approaches just so that we can explain it to the investors and other people who are going to use it. So
you'll actually have to give the investor, because he's not supposed to ideally understand everything, right? He's just supposed to see your equity curve and invest. So,
right.
Do they really demand for what is happening behind the scene also?
Yeah, they are demanding. Yes.
Okay. So, but do you all try out those kind of models, and any success rate if you could disclose?
So we are trying out deep learning, but we are specifically doing for NLP purposes. In stocks, we are not doing it because we are not able to figure out that how we are going to explain it.
Okay.
And I guess there are certain libraries that are coming up for explaining the deep learning.
Exactly.
Yes, but we are still not convinced about that. So it of course comes from the top to bottom, right? And then it's like a there's always a delay between what we believe and what investor we believe, and then we have to start pushing it aggressively. Then they will accept it. Also, what others are doing in the industry also plays a role, right? So it gets a bit difficult. Agree. And in game theory and multi-agent interaction, so we already talked about games. Mario, in Mario kind of environment, maybe it can be also applied to playing football. You might have seen Beautiful Mind. So game theory is evolved from that, and multi-agent interaction. So it can also be done to uh, so if there are a lot of agents participating in buying and selling of electricity, if it is given to reinforcement learning, it can actually find out ways to sell and buy electricity at lower price or higher price and make profit out of it. So we are talking about just one reinforcement learning agent, but then a lot of reinforcement learning agent can interact together with each other, and that can be multi-agent interaction. In robotics, it is it is done to find out the motor workings, the coding of the motor in itself, like how the motion will be, so that it moves certain things from one place to another in like least consumption of electricity.
Would multi-agent interaction be an analogy for ensembles, or it doesn't work like
that? In ensemble, as far as I know, we are trying to take the voting of different models for a given output. Both all are inclined towards predicting one thing. In multi-agent system, that's like a let's say 10 traders trying to make a profit, but our strategies are different, and there can be zero-sum games, right? Profit of one can be loss of others. So when I was referring to multi-agent system, like everyone is a competitor to each other, as far as I was talking about. But yeah, you can spawn an ensemble kind of reinforcement learning also, and give different kind of ways to optimize the thing. So one RL can be just based on random forest, and one RL can be based on DL and things like that. Yeah. In vehicle navigation, again, the vehicle has to go from one point to another, and it should not strike with people or trees or any other thing, and consume electricity or fuel as less as possible. So that's how it is being applied. So let's just go to the end of the slides, and we'll be talking about these two examples. So there are a lot of game applications that you must have seen, Atari games and Mario and whatnot. So there's this new thing that came up in 2018 by an Indian guy, and he trained the RL agent just so that the what you can say, the player can actually take free kicks. So it starts randomly, but then it understands from the reward that we can see here in the game. Based on that, it actually starts pressing the buttons in the power and the way that is required to put the goal into the place. So it takes the image as an input, extracts the features out of it, runs the Q learning, and then this OCR is done to just fetch the reward and use it to give the reward or the penalty to it. And then actually it improves, and we can see it over here. So it just tries randomly, but then it learns it, and then it also actually does left and right to get the view of the goalpost sometimes. And it also understands that if you are hitting these blue targets, then you are getting more reward out of it. And he has shown this chart where as more epochs are trained, the number of goals that you can put actually increases. So finally, it is able to put goals 50% of the times after 800 epochs. So if you see in this case that there cannot be a training data, right? So it will be just a brute force kind of thing कि ऐसे kick मारो training data बनाना है तो ऐसे तो though you can put the goal into the goal post, but from this, by just generating an input data randomly or in a particular way, you are getting a reward signal, and from that it is actually understanding. So it's supervised but not supervised kind of stuff. And there is this story about AlphaGo Zero. A lot of people have heard about AlphaGo. It was basically a algorithm based on deep learning created to beat the world champion in the game of Go. So what they did is they took the training data of the games played by the world champions. Basically, smart people are playing, then that's the best data to take, right? They won't take data of people playing like people like us who are playing. So they took the best data, best strategy data, trained a deep learning model over it. And once the algorithm was trained, then they spawned uh, two algorithms and allowed it to do self-play. So the algorithm was playing with itself, and it reached a particular level of ELO rating by which it was able to beat Lee Sedol. But then what happened in this case is that the bias of uh, the players, the strategies of the players went to the algorithm itself. So then it was limited by what it discovered, but just by how the how the people were playing. Then they tried out another thing where they didn't have any training data. They just spawned the one algorithm, RL algorithm, from scratch, and it learned on its own. Um, Basically doing self play from the starting itself. So in that, it's like it discovered that when actually you make a positive move, when you actually make a negative move, and in less data, in less time, in less processing power, it was actually able to beat the AlphaGo that beat the Lee, and so it was also called AlphaGo Zero because it started from scratch. So the power of reinforcement learning is that when there is no training data, there is no bias involved in it, and so it can achieve a maxima or minima that is better than the supervised learning stuff. So over here, the AlphaGo Lee that beat the Lee Steeler was trained on 48 TPUs, and the AlphaGo Zero was trained on only 4 TPUs, and it also, I guess, required less training days. So in less time and less data, it was actually able to figure out the right strategies and able to make moves that were not able to be understood by the humans who were playing against it. Or of course, humans were beaten by Lee, and AlphaGo Lee was like the algo having the strategies of the human. So it was able to beat those strategies as well. So by RL, in certain cases, we are going to be able to figure out new things that were not visible earlier. And there are also other things these people tried. So it was not just the self play from the scratch, but there are also other things. But majorly it was this self play from the scratch that made the whole difference. So yeah, that's all about ML, DL, and RL. And I also write this blog called ml-dl.com. Again, it means the same, machine learning, deep learning. So over there, I also write blogs on hackathons and how you can enter the data science industry, what people are looking for, and what are the courses you can pursue. So feel free to check it out.